Assalamu alaikum wa rahmatullah. Welcome to the 8th lecture of the course of probability and stochastic process. And before we start the lecture today, as we agreed last lecture, that we will start by solving, or at least show how to solve, the previous quiz. And the previous quiz was quiz 5. And you can see here that the first question is: random variable x has a uniform distribution from 1 to 2, then find the expected value of 1 over x. Find the expected value of 1 over x. Let us see how to deal with this question. I will just start by sharing the whiteboard so we can write. So now you can see that the question was that, okay, let me, one black. So we have uniform distribution. X is uniform distribution from 1 to 2, which means that it has this form from 1 up to 2. And of course, since the area under the curve must be 1, so here it will be also 1. Okay. And we like to find what is the expected value of 1 over x. Okay, this is, of course, this is x. We know that this expected value is the integration from minus infinity up to infinity, 1 over x times the distribution of x dx. The distribution of x is only from 1 up to 2. The other value is equal to 0, which means that it will be the integration of from 1 to 2, and the value of the function within this 1 to 2 is equal to 1, so it will be 1 times if x of x is 1, and then it will be 1 over x dx. Okay, so the integration of 1 over x equal to the natural logarithm of x, so it will be ln x, and this will be from 1 up to 2, and this of course will be ln 2 minus ln 1. Okay, and ln 1 is equal to 0, which means that this equal to ln 2. So the average of 1 over x is equal to the natural logarithm of 2. Okay, so this is the solution of the first quiz. Now, if we do we have questions here?
No.
Okay. If there's a question, I didn't hear that. So, but let us go to the second one. For the second question, that two independent random variables, x1 and x2, both are independent, both have exponential probability distribution function with lambda 1 equal to 1 and lambda 2 equal to 2. Of course, this was given already in the chapter and in the lectures. So I will write here, maybe easier. Okay, so it will for x1, it means that f of x1 is equal to lambda 1 equal to 1, means that it will be minus x, and for f x2, the distribution is exponential with lambda 2 equal to 2, which means that it is 2 times e minus 2x. Of course, forget this line. This is the problem that when you write on the PDF, but I will write it here. Again, x2 equal to 2e minus 2x2. So this is the distribution of x2, and this is the distribution of x1. The question here is find the probability distribution of y, where y is the maximum between x1 and x2. Actually, this was exactly given in the lecture, and also to show you where you can find it. So I will go to the lecture itself. So let me go here. Yes, share. Okay. Okay. So now to find the maximum, yes, this one actually. You can see here, find the general form of the probability density function of y equal to maximum between x1 and x2 as function of joint distribution. So it was given in this way. And actually, for the independent case, it was already given, as you can see it here. So it is it gives you the distribution of y should be the probability density function of y of x1, and you remove every x and you put y, and then times the cumulative distribution function of the second distribution, which is also exponential but with lambda equal to 2, and plus this one. So actually, I will go back to the lecture because it was already given, and the quiz is open book, so you don't need actually to derive the question again, but you should be able to substitute in the solution. So this it gives us in this way, so I will share it. So it was already given to you already, the distribution of y. It was given as that f x1 of y times f of x2 of y plus f x2 of y times the CDF of x1 of y. And the distribution of x is given, so it is e minus x, so it becomes e minus y times 1 minus, this is of course multiplied by 1 minus the CDF of y is e minus 2y plus, and this substitute here for the probability density function of the second random variable, which is 2e minus 2y times f of x1, which is 1 minus e minus 1. This is the distribution of y. And here it is also important to indicate what is the range of y, because actually x1 and x2, both of them are greater than or equal to 0. And also y is the maximum between them, which means that y also must be greater than or equal to 0. So this is the probability density function of y. The second requirement in this quiz, that to find the what will be the distribution of y that equal to x1 plus x2. Actually, this one also was given, and we show that the distribution of y will be the convolution between the distribution of x1 and the distribution of x2. I show you back where you find it in the book, in the chapter. So you can, sorry, I just repeat it again, the same. So this one, share, yeah. So in case that, I think it might be before or after, I'm not sure, I will check. Maybe. The independent, this is the maximum. Okay, maybe I will make search for that. Function, I go back. Yes. So this is the, you should use this one, as you can see in front of you. And what is f x1? I will write it here. That's it. Yes. So we know that what is this? That's f x1 So it is already the, as we mentioned, this will be the exponential distribution. So this will be E minus, instead of using x1, you put just y2 times f of x2, which is 2, multiplied by E of minus 2. And here you put y1 minus y2, then becomes you take the integration with respect to y2, and this integration from minus infinity up to infinity. Of course, here, because we know that y2, that every y should be from 0 to infinity, this one. So the integration will be from 0 to infinity instead of minus infinity to infinity. So, and I didn't ask you to solve this integration. Even solving this integration is easy because it is just exponential. But even I didn't request you to solve the integration, just to put it in this form. So anyone put it in this form, that he will get the points of this quiz. So it's as simple like that. Just substitution in the equation. Just you substitute in this equation of the convolution to find the distribution of of x1 plus x2. This will be the distribution of x1 plus x2. Okay. And sorry, the same, still need to be in the same. Yeah, but change to quiz 5. Yeah, so this is actually the second problem. For the third one is two multivariate correlated normal distribution with average was given as mu x1 equal to -1 and the average of mu x2 equal to 1. And then they gave us the variance of x1, the variance of x2, and also the covariance between x1 and x2. Okay, what that means? It means that now you have rxx equal to, this will be 4, and this will be 1, this will be 1, and this will be 2. So this is rxx. This is the covariance matrix as it is given here. Okay, and here what you need to do, just to go to the multivariate distribution, which was already given in the book, and just direct substitution. I show you how. So I go, let us go to the whiteboard to see, or before that, let me just show you where you can find it, the multivariate distribution. I will just search for it. Multivariate. Yes. So as you can see it here, so I want to see the general form. Yes. So actually, this is the general form, as you can see, of the multivariate distribution, whatever was the dimension for n dimension. So it is 1 divided by 2 by, here in this example, we have n equal to 2. So here because we have 2 independent, two random variable, so it will be n equal to 2. So 2 divided by 2 equal to 1. So the first thing that I will have 1 divided by 2 by times the determinant of rxx, okay, of the power of 0.5, okay, times e of the power minus half x minus mu x transpose times rxx inverse times x minus mu x without transpose. What that mean? The first thing, let us find the determinant of rxx. Rxx was given as 4, 1, 1, 2. What is the determinant? The determinant equal to, you multiply the main diagonal minus the other diagonal or the off diagonal. So it will be 4 times 2 is equal to 8. 8 minus 1 equal to 7. So the determinant equal to 7. So this will be 2 by multiplied by square root of 7, because here you have 0.5. Okay, and then we need to evaluate this term. So this term, forget now this minus half. Let us look to the others. So it will be vector. Okay, in the first vector, we have x minus mu x. So we have x1 minus mu x1. Mu x1 was given as -1. So it will be, sorry. Okay. x1 minus minus, it becomes plus 1. So the second element is x2 minus mu x2. Mu x2 equal to 1. So it will be x2 minus 1. So now this is the first element. Of course, I put it as a row vector because here we have transpose. Okay. Then multiplied by rxx inverse. So I need to take the inverse of this element, the inverse of this matrix. Okay. The inverse of this matrix for 2 by 2, I also gave it last lecture. So it will be 1 divided by the determinant of the matrix. Then you swap the main diagonal, so it will be, this will be 2 and this will be 4, and you take the negative sign for the off diagonal. So this will be the inverse matrix. So now you have, okay, let me remove this part because now I am looking only for this part. So here we have 1 divided by 7, and then I multiply this by rxx inverse, so it will be here 2 minus 1 minus 1, 4, multiplied by this vector. So this vector is x1 plus 1 and x2 minus 1. So what you have now, you have row 2. You have here one row by 2 element. Here you have 2 by 2. And here you have 2 by 1. So the result will be 1 by 1. The result will be scalar. Okay. So now if we solve this one, so it will be the first row times the first column. So it will be the vector of the multiplication of this vector times this matrix. It will be 2x1 plus 1 times 2. Then minus, because as I said, the first row times the first column. So it will be minus x2 minus 1. Okay, this will be the first element. The second element will be the same row times the second column. So it will be minus x1 plus 1 plus 4x2 minus 1. So this will be the result. This is the result of the first of this row times this matrix. But still we need to multiply this by x1 plus 1 and x2 minus 1. Okay, so you take the first element, you multiply it in the first element here, in the first element in this vector, and the second element in this row, in the second element in this vector. So the result will be, I will write somewhere, maybe somewhere here. It will be 2x1 plus 1 square. So it will be 2x1 plus 1 square minus x2 minus 1 times x1 plus 1. This is the multiplication of this element times this element. And now you multiply the second one times the second one. Then it will be minus x1 plus 1 times x2 minus 1 plus 4x2 minus 1 square. As you can see that it is a little bit long operation, but it is just high school math. So what you need here is to expand this one, x1 plus 1 square equal to x1 square plus 2x1 plus x1, all this multiplied by 2, and you just expand every element here. You make the summation of x1 together, the summation of x2 together, and the fixed element or the scalar together, and then you will find all the parameters of this quiz. So you can find, of course, now we found what is the value of alpha. Okay, here there is a mistake, so there shouldn't be square root here because they should be square here because we have n equal to 2. But now you can find here the value of alpha. We found it as square root of 7. Okay, and when you add all elements of x1 together, you will get the value of this a, and adding the elements of x2 squared together, you will have the value of c. And then if you add all x1 x2 together, you will have the value of b. And maybe I forgot here also to add d, but it is not a problem if you didn't do it, where d is containing the scalar values after this summation of all elements. Okay, and here of course we have 1 divided by we have already minus half, and then we have beta equal to 7. So here it will be divided by 14. So beta equal to 14. Maybe you can see that in this, this is the only quiz that it will need a lot of calculations, but maybe in the same time, it is the easiest one, because all what you need is just to find the inverse of 2 by 2 matrix. And after that, it is just multiplication of vectors and matrix, just multiplications and substitution. So here also is direct substitution in one equation. This one also is direct substitution in the convolution integral. Okay, actually I can see that the only one that it needs some thinking is this one. Even it looks the easiest one, but also it needs some thinking. Based on my experience, some students, they try to find the average of x and they didn't take the average over 1 over x. So it is a common mistake here. So if you did it, it is okay. I mean, it is quite common mistake that when they take the expectation of 1 over x, they take the expectation of x and then they substitute it. Remember always that expectation of 1 over x does not equal to, in general, 1 over the expectation of x. This is actually the target of this example. The target of this example, don't make this mistake. It is not equal. The expectation of 1 over x is not equal to 1 divided by the expectation of x. And actually, I remember that one student, he did this mistake in his master thesis because he was looking for to find the probability of error, and then he needs to make similar expectation to this one, where it was for example assuming that the received power is fixed, and then they assumed that the noise is random variable. Okay, so in this case, he received this signal to noise ratio becomes like fixed number divided by random process or random variable. So what he did, he take the expectation and then he make this expectation like in this way. Of course, all his results was wrong in that case, and he didn't understand why his results was not equivalent to what is known in the area, because we know, for example, the signal to noise ratio, as the signal to noise ratio increasing by some dB, then we will improve the probability of error. But based on his analysis, all his results was wrong because of this like simple mistake. But it is in the same time, it is simple by taking the mistake, but the results, the consequences of this mistake is really huge. They are not the same. This is not the same. So he or she needs always to take the expectation based on this way. So when you have expected value of 1 over x, this you must remember that is the integration of 1 over x fx of x dx. So even it is very simple, but I know that many students, they can like make mistake in this kind of problems. Okay, so that's all about the quiz. After the break, maybe I will start with 10 minutes after the break. Now I will come back to lecture. Actually, the break, we will start our break after half an hour. After the break, we can discuss more about this quiz and to hear from you your opinion about the quiz, the solution, and also how did you make the quiz? Was it close to the answer or far away? And I will be happy to hear your opinion about the quiz. But now let us go back to the lecture. Okay. Sorry that I forget to send you the updated version of the chapter. However, that I am still improving it and adding more numerical examples. However, that I will send it today after the lecture, inshallah. I will send you at least the latest version until I also add more and more numerical examples in this chapter. Okay. Okay, we have already covered this. This is about the characteristic function that we have already saw that, and this is Yes. This is the limits and bounds. Okay. Also, I like to come back to this limits and bounds maybe at the end of today's lecture or next lecture, because I feel that I didn't cover it well. So we will come back to that as well, which can be sometimes important. Okay. However, that's what I wanted to start, because after completing this section, the stochastic process, at least we have done with the minimum requirement for this course. This course, to say that you take course in probability and stochastic process, you should at least complete this section as well. After this section, we can say that we have done with the minimum requirement of taking the course. Okay, so this section is very important. What is a stochastic process? What is the meaning of stochastic or random process? Actually, what we have seen before, that it was dealing with a random variable. Okay, so what is the difference between random variable and random process? What is the difference between them, and what is the application of each one of them? Okay, so let me go to the whiteboard. Okay, now if you flip the coin that in your pocket, and then we say that this coin or a dice, for example, so we say that this experiment of flipping the coin, that it has some uncertainty. The outcome, it has some uncertainty out of this experiment. Okay. So when you throw the coin, then we say that we might have head or tail. And then we describe the outcome of this experiment, that if you get head, then this will be achieved with the probability B. And if you get tail, this will be 1 minus P. If this coin is fair, or if the experiment is fair, and then since we have only 2 outcomes, then the result P will be 0.5. So this is the maximum uncertainty that you cannot make any expectation of the output, because they will be 50-50. Okay, and also the same of throwing a dice. So the result will be like one of 6 faces. It can be 1 dot or 2 dot and up to 6 dots. And after that, we defined also random variable, and we say that the random variable is a real number representing the output or the event or the output of this experiment. So we can say that head is equal to 1, and for example, tail equal to -1. So then we will get 1 with the probability P, and then we get -1 with the probability 1 minus P. Or if then random variable is the number of dots when you throw die, then the output of this experiment will be 1 or 2 or 3 or 4 or 5 or 6. So this will be numbers. So we transfer or we make like mapping projection between the number of dots to real number. So now we have number 1, 2, 3 up to 6. Okay, so this is the random variable that and uncertainty. The process, or from its name, a process means that something like continue with some other independent variable. What I mean, for example, if you repeat the throwing or the flipping of this coin once every second. Okay, so you flip this coin once every second. Okay, and then the output 1 or -1, it can be voltage, it can be current, it can be any action that you are taking. So in this case, we have process. We have process with time. Here, time is not a random variable. Time is something that it is continuous by itself, and in the same time, it is independent of the process itself that we are doing. Okay, so now you throw the coin. Let's say that this is +1 and this is -1, and then the output is voltage, for example, between 1 and -1. Then the first flip, it can be 1. The second one is maybe 1. The third one becomes -1, then 1, then -1, -1, -1, then 1, and so on. So now it is continuous in time. What we call this? We call this a random process. Okay, we call this a stochastic process. Okay, because we don't know, it is flipping now between +1 and -1. The signal can be +1 and -1. Okay, and we have uncertainty here between -1 and the +1, but it is a continuous process. It is a continuous process, so it becomes process. It becomes a stochastic process. It becomes a random process. Okay, it is not necessary to be time, by the way. It can be assumed that there is someone, okay, that he is moving, and then he need to move and to jump during his moving between two positions, like +1 or -1 meter. So he need to jump every time between two positions. Now, what we have here, actually we have here distance. We don't have time. So this guy might select to jump here, first one, and then maybe jump here, then maybe decide to jump here, then jump here, and so on. So actually now it has distance. This guy is moving by jumping between two points. Okay, so now we have distance, and also this is a random process. Now this one is as well a random process, and it has discrete movement. Okay, is every random process discrete? Of course no. Of course no. I mean, the noise, for example, noise itself, this noise is a random process. This noise is a random process. Okay, so, and sorry, because this, it seems that it is okay. Okay, so this now is a random process. Information itself, information, that the signal that you don't know what will be, so it is a random process. Okay, this is a random process. And sine wave is not random process. Sine wave is not random process. Why? Because it is deterministic. Since it is deterministic signal and it is a periodic signal, so this is sine omega t plus phi a. So this is not random process. Why it is not random process? Because yes, it is varying with time, but varying in deterministic way. So this one is not random process. What else? Yeah, the prices, stock market, the prices of the shares, for example, if you look the prices of the shares for some company, for example, so the prices here is a random process. Okay, and we call it time series as well. We call it time series. Okay, but it's a random process. And what we are interested is to find the characteristics of this random process. Because if we know the characteristic of this random process, we will be able to expect what will be the next. Yes, it is random. We agree that it is random. We agree that it has uncertainty. But if we know what will be the distribution of this random process, then we can find what is the value in the future, what is the probability for the value to be between this value up to this value. The temperature in Benghazi today, or like during the year, that you have, for example, 356 days, and then we take the temperatures every day, the average temperature every day. So this is also random process. Okay, this is also random process. However, this random process is correlated. So if you want to expect the temperature tomorrow, you can use some probabilistic technique in order to find what will be the temperature between with certain confidence interval. So you can see that 95% the temperature will be, let's say, between 22 up to 25, for example. Okay, based on what? Based on the studying the stochastic process or the trend of the uncertainty in this time series. So now, what I want you to remember about stochastic process in general, that it is a random variable. It is a random variable. It can be discrete or continuous, but it will move and it will like act with time, will change with time, will change with distance, will change with any other like parameter. It can be within molecules, within on the quantum mechanics, it can be within the atoms, it can be anything. But if you have uncertainty, which is acting or moving or continuous or dynamicity, so it is dynamic with another independent non-random variable or non-random dimension, like time, like distance, we call this as a random process or a stochastic process. Okay. Before I come back to the lecture itself, I like to ask you, what is the mean of random process? So if we assumed that you went or you take a section in for example, Benghazi Sea, you go to the sea, and then every day you look to the waves on the, you take one picture, like sectional picture for the waves on the sea. Okay, so the waves on the sea will be something like that, for example. Okay, this is the wave at certain hour in day, for example, and then you came the next day in the same hour, and you take what will be the waves. Okay, and the third day will be the same. Maybe the fourth day it was windy, so we have large waves. Okay, and so on, and you repeat this maybe thousands of times. And this is the waves on that section of the sea within 1 hour, within certain hour. For example, let's say from 10 a.m. to 11 a.m. Okay, and you take picture and you have these pictures. Okay, now what is the probability that you will have exactly the same wave shapes within 2 different days? Of course, the probability here equal to 0. The probability here equal to 0 because it is a continuous process, but it is moving with time. Okay, it is moving with time. So what do you think about the mean or the average of this wavelength? Okay, now if you take the average within 1 day, we call this, for example, this is the waves in 1st of February. Let's say it was 2023. This was the 2nd of February 2023, and so on. So every day that we have the average. Okay, so now if you take the mean of these waves on the first day, so it will be here the mean, but remember here that this mean was only for the 1st of February, and this will be the time mean. You take the average mean over the time, okay, which does not necessarily reflect the randomness of this random process, but it can be valid for only for this 1 hour. So this mean, which is taken for 1 February, and it was taken for only 60 minutes. So now we need to incorporate the time information and the date information with this mean. So you cannot say that this is the mean of waves in Benghazi in that section. You cannot say that. You can say that this is the mean on the 1st of February in the year 2023, and it was taken only the mean over 1 hour. So this will be very restricted information here. You cannot say that this is the mean of the whole ensemble, the whole process. Okay, but let us take the mean over all these experiments that you done. Let's say you take it at time at 10:30 in the morning. So at the 10:30 in the morning, you take for all 30 days, February, okay, 30 days. So you take the mean here, so the mean here and the mean. So you take the average of all these means. So in this case, we call that this is the ensemble mean. Okay, you don't need here to put that the day because you take it over all days. Okay, but you need to add that this was taken at 10:30. So this is the mean taken at only 10:30, at the time 10:30. So you can see now that we have another dimension. Things is not easy anymore as before, that we just take the mean over the ensemble random variable. So now if you want to compute generally what is the mean of this wave's length. So here we assume that it is x. So what is the mean of x? So the mean of x will be the integration from minus infinity up to infinity. Okay. Before we were saying that fx of x and things was easy in this way. Now, unfortunately, you need to add x at time t and the distribution with time t, then dx. So what will be the result? The result will be the mean, but at time t. Every time now, it has different mean. Generally, of course. Now we will come later to some special cases. But generally, that every time you have different mean. It is not the same mean. The mean now is function in time. The mean now, the average now is function in time. The same thing that you can obtain if you talk about the covariance, for example. If you want, for example, if you want to compute what is the expected value of the power of this wave, for example, or x squared, this will be integration. Again, it will be xt, okay, square, xt square, fx of x and t dx. So this will gives you the expected value square, but it will be function in time. Okay, and also the variance, it will be function in time. So everything will be function in time because now the random process is a random variable, changing, but it is changing with time. After the break, we will come back to the chapter to see the special cases that we have. For example, what we call stationary. Stationary means that the random process is not varying with time. So if mu x of t is equal to mu x the same for any time t, then we call this process as stationary in time. If the variance is the same, we call it as like stationary invariance. If the correlation function, we will talk about the correlation function later. Okay. So before the quiz, let me just show this one. So if you like, now we have the random process. Okay, and this random process is function in time. So it becomes very, very important to study what is the average correlation between the same signal at two different times. At two different times, what is the correlation of this signal within the same signal? This is called autocorrelation, and the autocorrelation is given like r xx, but it will be at two times t1 between two times of the same signal. So this will be the integration from minus infinity up to infinity, x at t1 times x at t2. Then we have the joint distribution between x at t1 and x at t2. So I will just remove this one. Okay, f at x, it will be x at t1 and x at t2 and t1 and t2, dx at t1 and dx at t2. So you can see that don't be like scared from the equation. It is just descriptive, of course. Yeah, of course you will not see, or at least in this course, I will not ask you to solve such equations here. But we need to start from this general form. So the general form of the correlation between the, or autocorrelation between the signal with itself, where it is separated by 2 times T1 and T2, should be in this way. However, if the signal is stationary, then it doesn't matter where is T1 and T2. What is matter is only the time difference between them. For example, if you say that lambda equal to T1 minus T2, the time difference, then we can say that R x of lambda, because it is not important what is T1 and T2. What is important is only the difference between them. So in this case will be the integration from minus infinity to infinity. Then it will be x at t plus lambda, because it is a stationary process. So it will be the f of x at x. It will be of x t, sorry, xt, and then we will have the difference between them, lambda, and it will be dx. So it will be only the difference time between these two random processes. What is the application? What are the different simplification? Like, as I said, stationary. We have another simple simplification. It is called ergodic. What is the ergodicity mean? What the stationary mean? And what are the application, especially in electrical engineering and in communication? This is what we are going to introduce after the break, inshallah. So now we will take 20 minutes break, and we come back at 11:30, inshallah ta'ala. Thank you.
شكرا دكتور بطلافي.
Assalamu alaikum. Now we continue after break. We talk before the break about the concept, what is the meaning of stochastic process, what is the meaning of random process. And now we take one example. For example, here we assume that assume that we have a random signal generator that produce signal x of t, as you can see, and this x of t, it gives you 1 volt, 2 volt, 3 volt, 4 volt, 5 volt, 6 volts. So, okay, so actually I just take this example as that you throw the dice. So when you throw the dice, so you can get from 1 point up to 6 points. So now we assume that we have this signal, and this signal generates from 1 to 6 volts, that with a frequency of 1 hertz. What is the meaning of frequency 1 hertz? It means that every second it will like jump randomly to one of these like levels of voltage. Okay, so now if you throw or if you draw this die tossing random process, so you can see that this will be the output. So the output can be, as you can see, at the first time it was 1, the second time it jumped to 4 volt, then it jumped to 5 volt, it jumped to 6 volt, suddenly jumps to 1 volt and to 4 volt, and you can see that. So this will be the shape of the voltage output, that it is one realization. We call this as a one realization. Of course, if you repeat it, so you might get different realization of this random process. So now when you have this output or this time series, we call this as one time realization of this random process. Okay, so now we can call this random process as a function and 2 parameters. As you can see, it is a and t. T is time. Okay, this is time t. So time is not a random process. Time itself is deterministic, which is a continuous process. Okay, and then you have a. A here is meaning the event itself. So some books they wrote it like omega. So omega or a representing the random event. So we have a random part and we have deterministic part. The deterministic part is the time where this random process is acting, where this time process is acting. Okay, so now if you take certain time, if you, for example, if I come here, okay, at certain time, and then I look to this, what is the output here? So the output was 3, as you can see, and this happens at certain time tk. Okay, so this is when you have like a certain time, then you don't have random process anymore, because now you freeze the time at certain instant of time. So in that case, what you have is you have like random variable. Now we have a random variable. So for example, if we assumed that we have four dice experiment, okay, 4 dice experiment. So now everyone or every generator, it gives us certain time realization. If you put them like among each other, what will be the total sample space? So the total sample space is this one. So it might be the first signal generator gives you 1, the second gives you 1, the third gives you 1, the fourth gives you 1, or the first gives you 1, 1, 1, and the fourth one is 2. And you can continue in this way until 6, 6, 6, 6. So you can see that you have too many random or outcomes here that you can obtain. Actually, for everyone, it will be 6. So it will be large number of outcomes can be that from this experiment. So, but if you specify the time at certain time, so at certain time tk, and then you look to the outputs at that time, what you will have one of these outcomes. So maybe you can find that 1, 2, 3, 1. So at this certain time, when you check the outcomes, you find that the first generator gives you 1 volt, the second generator gave you 2 volt, the third generator 3 volt, the fourth generator maybe 1 volt again. So now we have one time realization. So now when we fix the time, what we have just a random variable, or a random variable containing the outcomes of 4 dice, the outcomes of 4 dice. But this will be valid only at certain time. Okay, so now you can see, I think we have a figure for this where we have them over each other. Maybe not here. Yes, you can see here. So now we have 4 outcomes, and then you can see this is the outcome of each experiment. Each experiment does not be as exactly the same as the others. For example, if you look to number 4, the outcome of number 4, it is clear that the updating rate is small. So here, for example, that maybe we have maybe 1 hertz, maybe 1, 2, 3, maybe we have 1 or less than 1 hertz. Okay, that in A3 we have faster changes. A2 we have also some middle between A4 and A3, and so on. So everyone, it might have different time characteristics, So this one, for example, for A1, it is clear that it has higher frequency or higher changes than the fourth one. Okay, and now if you specify the time, if you take at certain time, for example, at T1, okay, what you can see at T1, the outcome, as you can see, that I have for the first one, it was 1. For A2, we have 6. At 3, we have 4. And at the fourth one, I have 5. So now this is the outcome at time T1. So this is X at time T1. X at time T2, you will have different outcomes, and so on. So at each time, if you specify the time, you will have like random process, random variable. Random variable contains of 4 independent dice, as you can see here. Okay, now if you look to certain time, if you take one realization, so looking only to, for example, to number 1, then it means that we are looking for that realization. We are not looking for the different events. We are looking for a certain one event, and we take it over the time. We take it over the time. Okay. So now, if we go back to the equations, as I explained before the lecture, so you can see that actually all what we have seen in the random variable, we can apply them again in the random process. For example, if you want to compute the cumulative distribution function of any random process, what you need, if you remember that when we talk about cumulative distribution function, in general, we say that it is fx of, for example, let's say of x0, okay? And this equal to the integration from minus infinity to x0, fx of x dx, because this is actually equal to probability that x to be less than or equal to x0. This is what we used to have in the first part of this course, okay? Now, we have this process is changing in time. We have time series now. It is changing in time. So this one is not enough. This one is not enough to be used to define the CDF. How to define the CDF? We need now to say at what time. At what time? So, for example, if I asked you, I give you some like a realistic example that you can also think about. So if I asked you, what is the probability that the temperature in Benghazi, okay, to be less than or equal to 5 degrees? If I asked you this question, actually this question is not complete. It is not complete. The first question that you would ask me back, you say that in which month that you ask this question, because this question is not complete. For example, if the probability that the temperature to be less than or equal to 5 degrees, if it is in July, then I can say to you that this probability is almost zero or close to zero. This probability that can be like 10 of minus maybe 6, maybe within the last 100 years, it has not happened to be the temperature less than 5 degrees in July, for example. But if it is in March, or maybe it is in December, for example, then you can say that the probability that temperature will be less than or equal to 5 degrees at, for example, December, okay, this can be as high as, let's say, 10 of power minus 1. There's a chance 10% or 15% the probability of the temperature to be less than 5 degrees if we are talking in December. So now you cannot say general the probability to be less than or equal to. You cannot say that. You need to add the time information. You need to add the time information. I hope now that the connection is clear between the random process and the random variable. Temperature every day or per month, or the average temperature per month is a random variable itself. But at the same time, if you define the time, it becomes a random variable. If we define that the temperature in July, and we define July, that's it. We define July. Then the temperature becomes a random variable. So you can say that is what is the CDF of the temperature, what is the probability of this temperature, what is the probability density function of the temperature, and so on. So it is accepted, or it is accepted to be approximated as a random variable. But in general, if we talk about the whole year, then we need to define it month per month. Actually, there are some countries that the temperature, even within 1 month, should be dealt as a random process, not random variable, because it can change from the day and night. It can change from the day to day. Okay, so now I want you to connect the relation between random variable and random process. Random process, it means that this something is it is changing, but also it is changing with time. It is random by itself, but also it has some other changes with time which cannot be stationary, like the temperature with months. So when you say that the temperature is changing from month to month, it means that or the characteristic of the temperature is changing from month to month, it means that it is not a stationary process. It is not a stationary process. Okay, so now this explain why that the CDF we need to add the time information. The time information is important to be added, as you can see. So we add here TK to show that the time here is important, and this equal to the probability that X at TK, temperature at for example, February or at December. So it is important to add the time information in order to find the CDF. And since the CDF is function in time, of course, the probability density function will also be function in time, as you can see. So the probability density function will be for any random variable X, it will be depending also on the time of taking that experiment or looking to that observation. So TK here is also there, but of course we don't take the differentiation with respect to T, but we take the differentiation with respect to the random process X0, and then we define that X at X0, then we will have the probability density function, which will be also a function in time. Okay, and the mean itself, you can see, as I explained before the break. So the mean itself, as you can see, that it should be also function in time. So the mean, it is function in time. So now looking to the same example of the mean and the months. Here is the months, and this is the temperature, the mean of the temperature. Then we can start, for example, from January to February to March, and so on. Then this is the average temperature, for example, in Libya or in Benghazi. So it can be, for example, in January, it might be 15. In February can be, for example, 17. In March can be 20, and so on. So the temperature now is not just mean, not just average, but the average here is function in the month, in time. So because it is not stationary, it is not stationary. Maybe within 1 month, we can assume that it is a stationary as an approximation. For example, within, let's say, within July or within January, then we have, for example, within the 30 days or 31 days. So what is the average per day? So maybe the average per day is the same. So if the average per day is the same, we call that it is stationary within 1 month. The temperature is stationary within 1 month. Okay. You might ask a question. Now we are in November. This month we are in November, and today is the 26th of November. Okay. And what is the average temperature in Benghazi in 26th of November? How to find that? Based on observation. To find that, and you want to have like a reliable and good approximation for the mean at 26th of November, you need to go and check every 26th of November in the previous years. So 26th of November, 2022, 2021, 2020, and we go back maybe until, let's say, 1900 if we have record. Okay, so in that case we have 123 records. Okay, and then for this 123 records is the average temperature in every 26th of November in the previous 123 days. Then we take the average. So the average summation of those temperatures times in different years from I equal to 1 up to 123 divided by 123. This gives you like robust estimation of the average temperature in 26th of November. So now if you computed the average temperature in 27th of November, about tomorrow, okay, so if you take the same average over the all years before, all the records since 1900 until today, and you find that it is exactly the same average, then we call that it is stationary. So it is stationary on the daily basis. It is stationary on daily basis, but it is not necessary to be stationary in monthly basis. So 26th of November, it is not necessary that the average temperature will be the same as 26th of December, for example. Okay. Some of you may argue that actually even over the years it is not stationary, and I agree with him or with her if they say that, because now we have the global warming. The global warming now that makes maybe the average temperature before 30 years in November is not the same as the average temperature this year's in November, which means that it is not it is not stationary over time. Okay, it is not stationary over time. So in general, now when we talk about the expectation or the average in time domain. Okay, and what is the second moment? Actually, when we have random variable, we have only x. We don't have t information. We have only x, like throwing the coin, like dice, like many different applications that we gave before. So it is just random variable. Okay. So the second moment, we say that simply x squared. That is the second moment of this random variable, and this equal to integration x squared fx of x dx. That's all. Okay, and the variance of x squared equal to the expected value of x squared minus expected value of x all squared. So it will be the mean of the square values minus the mean value squared. This will be the variance, and we explained this before. If I asked you a question in random process, or you have random signal, okay, random signal or time series. So we have time series, okay, and in this time series, I asked you what is the expected value of x squared, what is the average power of this signal. You will ask me question directly that at what time you want to compute this average power. So the general expression of the second moment when we have time signal, it must be in this form. The expected value of x at t1 times the same x but at different time t2. So we have x at t1 times x at t2. This form is called the autocorrelation. This form is called the autocorrelation of the signal x of t. Actually, this is very, very important in time series or in random process. This is very important measure. It is very important measure. Why? Okay, when we have like random variable, not process, random variable x, then the mean of x gives you some deterministic value explaining or quantifying the fluctuations or the randomness in x itself. Now I have a class, and within this class I have 20 students, and in certain quiz every student get different mark out of 10. Some get 5, some get 10, some get 1, some get 3, 7. So those are like fluctuations. Okay, for someone who didn't look to the marks itself, so those for that guy, this will be like random process, that it is sorry, a random variable, 7, 6, 5, 1, 10. So it is a random variable, and those random variable, it can take any value, okay, between 0 to 10. So 0, 1, this is the marks up to 10. Okay, now I have 20 students. So those 20 students are distributed those marks over them according to their performance in the quiz. Okay. So the head of the school asked me, what is your average grade or the average marks? So I can't take the average. So the average is, I will sum all the marks divided by the number of students. So I gave them that the average was 6.8. Okay, so this 6.8 is like a deterministic number representing this random fluctuations in the marks of the students. But if in the same time, it doesn't reflect how scattering the students are. Because if all the students, 20 students, everyone got 6.8, then the average will be 6.8. But at the same time, if most of the students got 0, for example, if we have 7 students got 0, okay, and the other rest have like 10, maybe we can also get 6.8. But now the scattering is large. The scattering of the marks is large. So when I give the variance contains the information of the scattering of these marks. So as we have larger scatter of these marks, this indicates larger fluctuations in the marks or larger differences in the student. If we got this sigma x equal to 0, it means that we don't have any randomness here. So if I told you the average is 6.8 and the variance equal to 0, then immediately you know that every student got exactly 6.8 because we don't have any fluctuations in the signals. Larger fluctuations means that larger variance in the marks. Okay, so the sigma x square actually is one measure for the fluctuations or the randomness in that random variable. Okay, this is in random variable space. Now let us talk about random process. In random process, this autocorrelation is doing very similar task as the variance do in the, or as the variance does in the random variable domain. Here we take the expectation of xt1 and the xt2. This will be the integration from minus infinity to infinity. This is the general form. This will be x at t1, x at t2, and then we have the joint distribution of this signal between x1 and x2 at t1 and at t2. Of course, this is very general form. This very general form. So this is the most general form. We will see later some like simplified version, but this is the most like general and complicated case. Okay, what this means? Let me go to the whiteboard. Now we assume that we have some signal in this way, okay, and this signal is let's say that is random in this way. Okay, and now you want to compute the averaging of this signal at T1 and multiplied at T2. So this is, assume that this is T1 and this is the time at T2. Okay. So remember that this signal is only one realization. This is only one realization because now we can have infinity number as when I explain about November, 26th of November in every year. Okay, so this signal, you might have infinity number of this signal in this way. So you might have infinity number of the signals. Okay, so now when you have infinity number of these signals, then at each time, remember, at each time T1, you will have certain distribution of this signal. So we have distribution of this signal defined only at T1. And at T2, you might have completely different distribution of the signal at T2. At T3, you might have completely different distribution of the signal at T3 and so on. So at each time, you will have different distribution of the signal. Okay. Now I am looking for two different instances at T1 and at T2. Actually, in this case, we will have the joint distribution of the signal of x1 at T1 and x2 at T2. So we have joint distribution of the signal between two different time instances, which is the much more complicated case. Okay. However, fortunately, most of the signals actually that we are dealing in at least in electrical engineering and also in communication, we have what is known as a stationary signal. A stationary signal, it means that all these distributions are the same. So fx of x at t1 is the same for fx of x at t2 for all t1 and t2 belongs to some time period t. So in this case, the distribution is the same in this case. So in this case, we call it as a stationary process. A stationary process. Okay. The second thing that I wanted to say, even for a stationary process, if you want to compute the expected value of x1 times x2 in two cases, this is one case, and let us assume another case, expected value of x1 and times x2. For this case, actually, this is x. X was the problem that when I make a lot of a random signal, they will remove it, but I will try. I hope that will not be removed. Yes. It assumed that it is that I just wanted to take it off. So this is x. So maybe I will do it on the. Let me go to the lecture. Okay. Assume that we have such signal. Okay. This is the first signal, which has a lot of changes. And we have another signal. It has both of them, they are random, but this randomness is changing in this way. Okay. This is x1, this is the signal. Let's say this is x and this is y. Okay. Now I like to compute what is the autocorrelation of each one. So here I am looking for expected value of x at t1 times x at t2. Okay. And here I am looking for the expected value of y1 or y at t1 times y at t2. Okay. So what do you think? Which one should be higher? This one or this one? Of course, the expected value xt1 and xt2, the correlation here between x at time t1 and some time at t2. So sometime at t1 and at t2. Okay. I will use maybe another way, because this is very important concepts that I want to clarify these concepts very well. So maybe I will use maybe Word is better, or PowerPoint. Just a minute. Share. Yes. Let us try the whiteboard of the Zoom itself. I hope that will work better. So this is for random process X, and another one for random process Y. And this one, as I said, we have the signal which has changing very high, very large change in this way. And the other one, it has lower randomness. So in this case, it changes as well in this way. So, but it is not. Okay. And this is at time t, and this one at time t as well. Okay. So maybe the expected value of x at t, it might be the same as the expected value of y at t. Okay, assume that they are similar or very close to each other. Okay, so the mean itself, the mean over time, both of them, they have the same mean. Maybe they are stationary, so you don't need to put t, or non-stationary, so you can put t like this, but it doesn't matter. Okay, so now the mean is the same. However, it is clear for you, as for me, that the randomness in x is more than the randomness in y. So in x, we have larger fluctuations, larger randomness. Okay. In y, we have more smoother. It is random, but it changes slowly. Okay. So now, if you are in any time t1 and take another time t2, and in the same way, take time t1 and take time t2. Okay. So the expected value of this signal x at t1 times x at t2 is called the autocorrelation between these two times, t1 and t2. And also for y, for the second one, the expected value of y at t1 times y at t2, it gives you the autocorrelation between two times t1 and t2. So this could be written like r xx t1 and t2, and this written as r autocorrelation yy between t1 and t2. So if I ask you a question now, which one you think that it is larger? If this is rxx or ryy? The autocorrelation means that the relation between the signal at t1 and with itself after some time at t2. Okay, it is clear that the autocorrelation in the case of x, it will be less than the autocorrelation in the case of y. Why this happened? Because the autocorrelation, it measures how much they are related. The signal at t1 and at t2. So it is clearly that because in the y case, in this case, the changes is slowly. So the relation between the signal between t1 and t2, it will be higher than the relation of this very fast and random changes between t1 and t2. For example, in the case of y1, I can estimate the future much better than the case in x. For example, if I am at t1, I like to estimate what will be the signal at, let's say, t3 here. It becomes easier because now I am at t1 using the autocorrelation function. I can estimate what will be the signal or extrapolate the signal at t3. But here, if you are at t1 and the signal at t3 here, so it becomes much more difficult to estimate or extrapolate the signal after some time. Why? Because the randomness in this signal is more than the randomness in that signal. Okay. Now let me try to draw the correlation or the autocorrelation as a function in time. Okay. So as a function of time, I can draw for the x case. This is rxx. So the case can be something like that. Because we have high correlation. So this is lambda. Lambda here is equal to t1 minus t2, the difference in time. Okay. So here the relation, because for example at 0, you will have the highest relation because the signal with itself is the highest relation. As you move from 0, then the correlation will decrease until it might becomes like uncorrelated after some time t. But in the case of y, lambda, and this is ryy, that because of the high randomness, is it like that, or maybe sorry, actually the high randomness was in x, not in y. Sorry. So I will yes. So this is, maybe I can do it this way. Yes. Actually, this is the RYY maybe, and this is RXX. Sorry, because I just reverse in the different way. So in Y it was very slowly changed. So it was very slowly changed. So it means that the correlation is like this one. So the correlation takes time. But in RXX it was changing very fast. So the correlation was little smaller, like this one. So this means that the correlation is very narrow. It means that because X changes very fast, like this way. So after small time, very small time, from any time, if you start here, after small time, you will lose any correlation with the signal. You will lose any correlation with the signal. But in the first case, because Y was changing much slowly, so it means that this is the signal in time. It is random, but it still changes around very slowly. So if you are at certain time t, so the signal highly correlated even after some time t2, where here is lambda, the difference between times. So this represented by this way. So the correlation, if the correlation is flat, it means that it is highly correlated with time lambda, or the difference time lambda. If it is narrow, as it becomes narrower and narrower, it means that it becomes like the correlation becomes lower and lower, the autocorrelation, until we reach to the extreme case. What is the extreme case? The extreme case when the correlation becomes equal to delta of lambda. What is delta? Delta is the direct delta function. It is not function, but they call it function. So it is like direct delta. This direct delta is defined as infinity for delta equal to 0, and equal to 0 for delta does not equal to 0, and the integration of delta of lambda from 0 minus to 0 plus d lambda equal to 1. It means that the area under direct delta equal to 1, this is the area equal to 1, but it is undefined at delta equal to 0. What that mean? It means that this function, if you have function with autocorrelation function, is given as delta, it means that we call this uncorrelated process. We call it as uncorrelated process. What is the meaning of uncorrelated process? It means that if you know the signal at any time, for example, at time t1, even you know all the history from minus infinity up to t1, you will never be able to estimate what will be the signal after t1. Even t1 plus 1 microsecond, you cannot estimate it. The best estimation of the uncorrelated process is mean. For example, if we have Gaussian signal with 0 mean, and it was uncorrelated process, then since it is uncorrelated process, so the best estimation is 0. So even it was changing like this way in time, but you will not be able to estimate or to extrapolate the signal at any time, regardless of the collected samples of that signal. So in this case, we call it as uncorrelated process. So the correlation actually is very important. The correlation gives us the information on how the signal or the randomness of the signal is changing with time. Okay. Okay, let me first remove. Okay. So you can see here that we can see, for example, how to find the commutative distribution function. So in between these two joint process, so you need to take the time into consideration, as we said. So it will be the probability that x at t1 to be less than or equal to x1 and to be less than x2. Then we can find the joint distribution of this process by differentiating by the double differentiation of this probability density or OCDF of this process. But let me now, this is the way how to compute the covariance in the random process. So the covariance is the expected value of x at t1 minus mu at t1. Now we are talking in general way. Times x at t2 minus mu at t2. And this gives us the autocorrelation between t1 and t2 minus the multiplication of the mean process at t1 and the mean process at t2. And of course, if we have zero mean in any of the process, then the covariance will be the same as the autocorrelation. After that, we have example. Consider a time-varying random voltage generator that produces voltage level plus or minus 1 volt each second. It generates these levels based on the probability distribution. So this is the probability that you get 1 volt for each second. So this each iteration. So for example, if you start with iteration k equal to 1, it will be like 1 plus 1 equal to 2, 1 plus 3, 1 plus 2 equal to 3. So it will be the probability to be 2 divided by 3 to get 1. And then fourth iteration, you will get also, you can compute the probability in each time. Okay, so then the probability of course of the voltage to be minus 1 will be 1 minus the previous probability and gives you this way. So now you can compute the mean or the average here. It will be plus 1 times the probability to get plus 1 minus 1 times the probability that you get minus 1. So this is the mean. And you can see that the mean is time varying. The mean depends on the iteration. For example, if iteration equal to 0, then the mean equal to 1. At iteration equal to 1, the mean will be 1 divided by 1 plus 2 equal to 3. And then you can compute it is 1 over 3. At k equal to 2, that will be 1 divided by 2 times 2 equal to 4. 4 plus 1 equal to 5. So the mean will be 1 over 5 and so on. So as you increase, you can compute the mean at each time. So the mean is time depending. And also you can calculate the autocorrelation of this process. So the autocorrelation between k and k equal to the expected value of xk squared. And this gives you, so the correlation here equal to 1. The autocorrelation equal to 1 at the same time. Okay. The autocorrelation at different time, k and m, where k does not equal to m, gives you this relation. So this is the autocorrelation for any k and m. And also you can compute the covariance. So you can see here, in this simple example, when we take discrete time, that the mean, variance, correlation, autocorrelation, everything is function in the time iteration k. And here we wrote code to generate this process and to compute the mean and variance, and then we approve that they are the same. Okay. The second case, which is very important that we need to cover today, is the stationary process. A stationary process, as I mentioned, when you have the parameter of the mean and autocorrelation and those things are not function in time, explicitly in time. I mean, for example, if the mean, as you can see here, is equal to mu x, and mu x is not function in time, as you can see, now we don't have time. So at any time, it will be the same mean. So we call this as a stationary process. Okay. And also, if the autocorrelation at T1 and at T2 is the same as the autocorrelation at T2 minus T1, regardless where was T2 and where was T1. For example, if T1 equal to 1 second, T2 equal to 3 seconds, so the autocorrelation Rxx between 1 and 3 will be the same as Rxx of 1000 and 1003. So as far as the difference is this one, 3 seconds, okay, or then it will be the same. as the difference here, maybe it could be maybe at 2 actually, or maybe yes, this one. So it should be 1001. So the difference between 1001 and 1003 second is the same as between 1 and 3. What is important here is the difference in time. It doesn't matter where you take this time, but the difference makes the difference. Okay, so here lambda equal to T2 minus T1, regardless where is T2 and where is T1. This now called stationary. If all moment means that expected value of x, expected value of x squared, expected value of x cubed, all moments, they are not function in time, we call this as strict in or stationary in the strict sense. Stationary in the strict sense. In other words, it is when we say that fx of x and t is the same for any t. So it is equal to fx of x. So it is not function in t, or it is the same at any t. So we call that stationary in the strict sense. However, it is hard to approve that all processes in physics, they are strict or stationary in the strict sense. However, in the wide sense, only the mean and the correlation, they are not function in the actual time. Only the mean and the correlation. This is called stationary in wide sense. Stationary in wide sense. Fortunately, in wireless communication or in telecommunication in general, also in many other applications, we can approve that these processes could be considered as stationary in the wide sense. Actually, stationarity in wide sense simplify the analysis. It will simplify the analysis. Otherwise, we will have these complicated relations. Otherwise, we will have such complicated relations that you need every time to know the joint distribution between T1 and T2 and taking the function at certain T1 and certain T2, which can be very complicated, and sometimes it is even untractable or infeasible to solve. But fortunately, that most of the process can be stationary process. Okay, now we can talk also about even simpler form, which is called ergodic process. Ergodic process, what is the meaning of ergodicity? Okay, actually ergodicity makes the dealing with the random process much easier than before. Okay, why? I will give this one and then we end today's lecture, but it is very important to understand the meaning of ergodic process. It is extremely important to understand them, because actually you will deal most likely in your master thesis or in your PhD, most of the time actually we deal with ergodic process, because it is much easier than even stationary. It is much easier to handle. Okay, what is the ergodic process? Let me go back to the whiteboard. Okay. Yes. So the ergodicity, as in the beginning of this lecture, I talked about the random, this random changes in time. Okay, and I said that you might have infinity time of realization of this process in time. Okay, so we have here x1, here we have x2, and maybe we have up to xn. We might have infinity number of realization in time, as you can see here. And also we mentioned that now when you take the mean, so you have to define the mean at what time? At T1, for example, the mean at T1 or the mean at T2, or the correlation. And then we have these general forms that we have already seen, which I said that it is very complicated to deal, especially that if you are working in a real problem. Because if you want to build this, the section of the wave, as in one of the cost area, for example, you will need to collect like thousands of them in order to build like large enough ensemble in order to find the characteristic function or to find the probability density function at each time of the year and blah, blah, blah. So it can be a lot of complicated things here. The ergodicity or the ergodic process, the ergodic process tells us that if, sorry, okay, the ergodic process say that it is enough. Just focus and concentrate with me about this point. That if you take any of these time realization, if you take any of this time realization and compute the mean and correlation of this time realization, it will be the same as the ensemble mean and autocorrelation. What does that mean? You know that the expected value of x we set at time t equal to integration from minus infinity up to infinity x at time t fx of x at time t dx. This is what we show in general, and we said this will be mu x at time t. This is the general case, okay? This is the general case of non-stationary process. And the same way, the same one will be equal to mu x without t. This will be in stationary process. This is in the general case in non-stationary process. Okay. The third case, the most simple case, it says that if you take the expected value as 1 divided by time t, integration from minus t over 2 up to t over 2, x, any of those, x1 or x2 or x3, so I will say xi of t dt. Okay, so now you take only one time realization of these signals and you take the average over time, as you can see, from minus t over 2 up to t over 2, okay, dt. If this, sorry, wait, just a minute. The whiteboard disappeared, so I need to reshare it again. Yeah, so this equal to, if this one is equal to the same as mu x given above, this one, then we call this process as ergodic process. We call this process as ergodic process. So now just what we need is simply that equal to, we take to take okay, to take the limit, sorry. Okay. Is equal to the limit when t becomes large enough, okay, 1 over t, and then the integration from minus t over 2 up to t over 2, okay, xi of t dt. So if this gives us the same mean, then we call this as ergodic. So what that means, or what is the benefit of this ergodicity? The ergodic process, it makes it much easier because now you can take only one time realization and then you compute the mean of that time signal and you compute the autocorrelation, because will be the same also for the autocorrelation case. So R XX between any time t and t plus or minus lambda. In other words, we call it like Rxx of lambda, okay, equal to the same as we take like large time t goes to infinity, integration from minus t over 2 up to t over 2. Then we have x, okay, of t times x of t plus lambda. Then we have it dt. So now you take it in time. You can see now we don't have the probability density function. We get rid of probability density function in computing the mean and also in computing the autocorrelation. We take one-time realization. For example, if you have a received signal antenna here, and then you have a signal arrived to you, which has some time t. For example, you collect, let's say, 1 minute of this received signal. Then from this 1 minute, you compute the mean of the signal, x, expected value of x. It gives you the integration from minus t over 2, then x of t dt. Actually, this is low pass filter. The output, it gives you the average of the signal, and also you compute the autocorrelation function of lambda, and you can claim that this mean and this correlation function are the same if you compute the mean over the real mean. Actually, the real mean, the actual mean that you need to compute over the probability density function. From minus infinity up to infinity, x times fx of x dx. However, remember, this distribution is not easy to find. Even without t, even it is a stationary process, is not easy to find. If it is not a stationary process, it can become even much more complicated to find in practice. I mean, maybe in math, you can do whatever you like in math, but in reality, it is hard to find this probability density function, especially if it is non-stationary. And even when it is stationary, to find it is not easy. Of course, we can give some assumption that we can say that it is normal distribution, it is multivariate distribution. We can say whatever we want as assumptions. However, it becomes much easier if instead of making the averaging over time over probability density function, we make the averaging over time. Over time, we have it already. We have the signal. Maybe you store the signal, and then you take the averaging over time from t over 2 up to t minus up to plus t over 2 x of t dt. It becomes much easier. Now, if they are equal, if they are the same, then we can call this process as ergodic process. As ergodic process. So now we should understand, or we should have learned something. When I give you signal, and I told you that this signal, it has the output voltage like -1, 0, 5, 7, 10, 3 volt. And I asked you, this is at each one at certain time, at certain sampling time. For example, T0, at T1, at T2, at T3, at T4, and at T5. So I asked you, what is the mean of the signal? You will say that, okay, it is easy. The mean, μx equal to -1 plus 0 plus 5 plus 7 plus 10 plus 3 divided by how many that we have? 1, 2, 3, 4, 5, 6 divided by 6. So you will say that 7 plus 3 is 10, 10, 20, 25, 24. So it will be 24 divided by 6, which equal to, you say that it is 4 volt. Okay. Now you should understand that this mean or this calculation is correct if the original signal is ergodic. Okay. If it is not ergodic, this calculation is not correct. As a general mean, it will be the mean of this sample in front of us. It is okay. If I told you, calculate the mean of only the signal of this signal, this is okay. You can do it in this way. But if I asked you to find the mean, the general mean of this source V, which generates this signal, if you do it in this way, that you take the summation of the signal divided by the time, because here everyone multiplied by delta t, and here we multiply by delta t cancel delta t. So we have this summation directly. So if you made it in this way, it will be incorrect in case that the signal is not ergodic. But if the signal is ergodic, then this calculation is correct. And if you go to the research in the area of wireless communication, I can't say 100%, but I can say at least 98% of the research is done assuming ergodicity process. They take the average over the time, they compute the correlation over the time, and so everything is computed over time. Okay, so now it should be clear this main concept of okay, let me go back to the lecture. So because I don't want to take more time from you, so I know that we went through different topics today, but the conclusion that I want you to remember from the lecture today, that in random process, it means that the random signal or the random variable, it is acting in another dimension. It can be time, or it can be space, it can be location, it can be any other non-random dimension, and it is acting. There is dynamic changes, okay, and then we have process. In this case, we have stochastic process, and out of this stochastic process that we need to study this stochastic process. And when we study this stochastic process, we define the general study where we can find the mean of this process, and also the correlation or the autocorrelation of this process, or the cross correlation of this process. And we said that the mean, average, or correlation or cross correlation, all of them will be function in the time, will be function in the time instance where you take this process. Then we come to easier or more simplified version, where we talk about stationary process. And the stationary process tells us that this process, the mean and correlation is not function in time itself. So the mean that you find at any time will be valid for other times as well. Okay, so in the beginning we have the non-stationary process. Inside, as part of it, we have the stationary process. Okay, and finally we have the ergodic process. So the ergodic process, every ergodic process must be stationary. Okay, so every ergodic process must be stationary. So we don't have ergodic process but non-stationary. Of course, it must be stationary first, and after that it can be ergodic. So the ergodic process, it says that if we take the average over one time, it will be enough. We don't need to find the probability density function of the process itself in order to find its characteristic function, or it is like behavior, like mean and autocorrelation, covariance, all these things that we can deduce them, or we can extract them from one time realization, long enough time realization of that process. Okay, long enough time realization of this process. And also I give some examples. For example, the temperature, it is a clear example that for non-stationarity. So the temperature is non-stationary process, because the average temperature as I said, in December will be not the same as the average temperature in July. So it depends on time, which makes, in this case, non-stationary process. So you can see here, this is the mean. So the mean can be taken over the time, and also the correlation function can be taken over the time. And in next week, inshallah, we will talk about the spectral density, the energy and power spectral density, because if you want to submit some information, so the information, whether was voice or image or whatever, it has also some random changes, because if it is not random, there is no information. If it is not random, there is no information. For example, if you want to send cosine omega t, why you send cosine omega t? You can tell the receiver what is the frequency of the cosine, and it can be generated there. So when you send something, it means that you send information. Since there's information, it means that it has some uncertainty. Since there is uncertainty, then it is a time series. So it is a random time series. It is a random signal. Okay. Now the question which is very important: what is the frequency domain of this random signal? What will be the frequency domain in this random signal? Because I need to know the frequency domain, the bandwidth, in order to design my communication system to submit this information. So this will be the topic, inshallah, of the next week, where we talk about the how to convert the power spectral density from the autocorrelation function. We will see that taking the Fourier transform of the autocorrelation function, it gives you the power spectral density, which contains the all frequency content of this random signal. So, and also we define what is white noise, what is the impact of the white noise in our communication system or in electrical engineering systems in general. Okay, so that's all. Maybe I go in some details, but actually, as I said, the message that I wanted to say in this lecture today is just to it is one of the four issues that they are very important. The first, to understand what is the meaning of random process and stochastic process and the difference between random process and random variable. The second, to at least know in general how to find the mean and variance and the autocorrelation in case of random process. The third, the simplification of stationary and what is the impact of stationary over that. And finally, the ergodicity and the ergodic process and how things becomes much easier. Next lecture, inshallah, we will go to the power and energy and power spectral densities of the random process and how to apply this in order to design our filters or our communication system. That's all for today lecture. As I said, today lecture is very important, and we continue for this for the coming at least 2 weeks, inshallah. Thank you very much. And if you have any questions, you can ask, and I will stop recording now. Yeah.